Hi. Okay, so let's talk about the compact beams. And this topic was already covered before your spring break, but I just want to review it quickly and then move on to the next topic. So let me show you the slide. Okay, here we have the PowerPoint. So we already talked about the compact beams in our class, and the compactness in the steel design is defined as, this is for beams by the way, is defined as this. The flange width to thickness ratio is the key information to determine whether your beams are compact or not. So as you can see in this equation, here we have two quantities. One is BF and the other one is TF. And this is actually BF over 2 to TF ratio. So let's say here we have a Y flange beam. Sorry about my poor drawing. Not familiar with this yet, but anyway. So BF is the entire width of the flange, and TF is the thickness of your flange. And BF over 2 means from the center line to the edge of the flange. So this is the length of this cantilever portion, right? So length, which is the flange width, to the thickness ratio. If that ratio is less than 0.38 times square root of E over Fy, E is Young's modulus, 29,000 KSI for steel. Fy, depending on the material property, but we mostly use a 50 KSI steel. So on the next slide, this equation is coming from the same relationship, but when I plug in 29,000 for E and 50, both are in KSI for Fy, and simplify it, then you will get this relationship. So bottom line is, if your width of the flange, so whenever you open up the steel manual and pick a section, pull up the value for BF, the width of your flange, and thickness of your flange, plug those two numbers into this relationship. When you satisfy this, then your sections is classified it as a compact beams. So what does that mean? So that means the compression flange is not going to be buckled locally before the beam reaches its full capacity. Full capacity means the plastic moment capacity. So we already talked about that. We already talked about the Z value. What is Z? Z is the plastic section modulus. So this is the plastic moment capacity, and P is equal to Fy times Z. So Fy, the yield strength of the material, in Z. So Fy times Z, the MP is going to be the maximum nominal value of your moment. And this is, by the way, when your beam is laterally fully supported, which means whether your unsupported length is going to be 0 or less than L sub P. So I'm going to skip this discussion. We have a compression zone and a tension zone. There is a fight between tension and compression, and they compromise. So this is the final failing mechanism. We talked about this before. So lateral torsional buckling, we have a movement transition, but we also have a torsional movement too. So the rotational movement and the transitional movement, combination of those two is called the lateral torsional buckling. Okay, so the most important chart is this. Let me just go on to, yeah. So this chart, which is very similar to the column buckling chart, right? We have yielding and then inelastic buckling and elastic buckling. This is exactly kind of the same. So we have a fully plastic moment, and here we have nominal moment is kind of reduced due to the lateral torsional buckling effect. And if your unsupported length is too long, then longer than L sub R value, then your nominal capacity of your beam is pretty low.